Hi everyone, thank you for joining my presentation on fast and reliable missing data contingency analysis with predicate constraints. My name is Xu Niang. I'm a PhD student from the University of Chicago. Real-world datasets are rarely perfect. They could be stale due to wrong entry or out of sync with the latest updates. Even worse, the data could be incomplete or partially missing due to, for example, file system corruption or network outage. The key question of dealing with missing data is to estimate its effect on the result. Analysts could extrapolate using the existing data, and this method works well only if missing data has a similar distribution. They could also rely on their experience or beliefs on the missing data. In this example, we have an order table that's partially missing. Each order has three attributes: date, city, and price. Suppose we have an important decision to make based on a revenue, but because of missing data, this simple decision is hard to make. Of course, there's nothing we can do if we don't have any more information to support our decision making. Luckily, from our experience, we do have some beliefs like the number of orders between November 7th and 17th should be no more than 5,000, or the largest price between November 5th and 10th in Chicago is no more than $99, and there are no more than 1,000 orders, and so on. To utilize these beliefs, our first challenge is to encode them in a formal and logical way for us to reason about. The second challenge is that these beliefs could be overlapping and conflicting arbitrarily. How do we derive any reliable conclusion from them? Existing techniques can be roughly classified into two categories. The first approach derives results from a model based on existing data, which assumes missing data has a similar distribution, but that might not always be the case. Also, it is hard to specify our assumption probabilistically, and it is hard to quantify uncertainty. The second approach models missing data with an incomplete relation model, for example, C tables and M tables, but it's hard to use them to quantify effect on aggregate query results. In this work, we address these two issues in existing work by defining a formal language for specifying beliefs and a reasoning algorithm to calculate result ranges possible under these beliefs. Our framework can be used to solve min, max, count, sum, and average queries. We also propose optimization techniques for better efficiency. We will focus on the language and the framework in this talk. Our language is called predicate constraint. It is a triplet of predicates, frequency constraint, and value constraints. Predicates filters the tuples in a dataset, and the tuple satisfies the specified constraints. One of our aforementioned beliefs could be encoded like this. We use the conjunction of predicates on data and city as predicates, and specify the frequency constraints and value constraints accordingly by our belief. We could also have a set of pieces. The simplest form is where the predicates of pieces are disjoint, as shown in this example. In this case, answering a query is simple. We just need to find relevant pieces. In case you are wondering, yes, a histogram is a special case of a PC set. Now that our beliefs are encoded in a set of pieces, any answer derived from them must not violate any of the constraints. And as we mentioned earlier, the challenge is that pieces are overlapping and conflicting arbitrarily. Before we dive into details, I'd like to emphasize our wording of contingency here. Our analysis is based on a set of beliefs of the data encoded by PC. Any conclusion is based on the pre-assumption of such beliefs holds true. And of course, our analysis could draw different conclusions if the beliefs change. We believe contingency analysis perfectly describes that. Plus, our framework has the following desirable properties. Pieces can be easily verified, and they do not rely on existing data. Our framework reconciles conflicting constraints and can generate the optimal and deterministic results. With that in mind, let me introduce our PC solving pipeline. The first step is called cell decomposition. This step takes a set of pieces and our target query as input. It generates a set of disjoint cells for later use. To do cell decomposition, we first express each cell as a conjunction of PCs. For example, here we have C1, a conjunction of PC1 negate PC2 and negate PC3. C2 is a conjunction of PC1, PC2 and negate PC3. C3 is a conjunction of negate PC1, PC2 and negate PC3, and so on. We can note that the number of cells is exponential to the number of PCs. In the next step of cell decomposition, we need to find out which cells are valid. For example, if two PCs are disjoint, then their conjunction will be false. We use a set solver called Z3 to evaluate each cell. Because the number of cells is exponential to the number of PCs, we propose three optimization techniques: DFS pruning, expression rewrite, and early stopping to reduce the cost of cell decomposition. You can find more details in the paper. In this example, we use a synthetic dataset of three attributes, A, B, and C, to demonstrate how to solve queries with PC. The predicates of PCs are on attribute A and B. From the plot, you can see that the two PCs partially overlaps. Answering any query here means to find out the possible range of the query result, i.e., the upper bound and the lower bound. Of course, trivially, negative infinity and the positive infinity can bound anything, but they are useless. In this example, to answer a sum query on the C attribute with PCs, we first decompose the two PCs into three disjoint cells, C1, C2, and C3. Then we construct an integer linear programming problem. We focus on the maximum problem here that represents the upper bound of the query result. The lower bound can be solved by negating the constraints and also solve a maximal problem. Our objective here is to maximize the number of tuples we assigned to each cell times their corresponding value constraints. Our assignment to each cell is subjected to the corresponding constraints of that cell. The IOP problem can be solved by any off-the-shelf solver, and the solution represents an assignment that can maximize the total value, and that by definition complies with all specified constraints and is an optimal solution, i.e. a tight hard bound. Other aggregate queries can be solved similarly. For example, for count query, we need to modify the objective here to get rid of the value constraint. You can find more details in the paper. The previous example is simple enough to be solved by trial and error, but that doesn't mean the problem is simple to solve. In the paper, we show that we can reduce the maximum sum problem to a maximal independent set problem. Now we have our PC solving pipeline ready for a single table. We extend PC to multiple table to solve aggregate queries with inner equal joins. You can find more details in our technical report. In our experiment, we simulate a missing data scenario by removing some data from the table, and we feed each baseline with some information. For example, sampling baselines get some samples of the missing data, and PC baselines get some PCs that describe the missing data. We set up our experiment to compare our PC baseline with sampling baselines. For sampling baselines, we have uniform sampling and stratified sampling, and both applies a 99.9% confidence interval. For PC baselines, we have core PC, which is a PC baseline that utilizes a set of PCs whose predicates are correlated to the workload, and random PC, which utilizes a set of randomly generated PC. We also use a baseline that uses a histogram built on the target attribute of the sum query. We give each baseline a similar amount of information to generate a result range. Our first metric is the failure rate, which measures how often the result range fails to bound the ground truth. Our second metric is to measure the accuracy in terms of the overestimate rate, which is the ratio between the result and the ground truth. In this experiment, we use 1,000 sum queries generated on the Intel wireless dataset to evaluate the baselines. Both of the x-axis shows the fraction of data missing. The y-axis on the left figure shows the failure rate. As expected, because PC baselines are generated to comply with all constraints, we have a zero failure rate.
The y-axis on the right figure shows the median overestimate rate of the 1000 sum queries, and it shows that PC baselines are competitively accurate. On the other hand, failure rate of the sampling baselines increases with the fraction of data missing, and that's because the sampling baselines and other statistical approaches are optimized for expected accuracy, but not for extreme behaviors, and that introduces failures.
In this experiment, we further compare the uniform sampling baseline with PC by varying the confidence interval of the uniform sampling baseline. You can see that the failure rate of the sampling baseline decreases as we increase the confidence interval, which is expected. However, the overestimate rate also increases, and that indicates a trade-off between the two metrics. We should know that it is not really fair to compare the accuracy of PC with sampling baselines, because sampling baselines cannot achieve a zero failure rate that is guaranteed by PC. But nonetheless, our experiments show that the accuracy of PC is competitive. As a conclusion, in this paper, we propose a novel constraint language called predicate constraint that can be used to express our beliefs on the missing data. PC can be easily verified, and with our framework, we can derive deterministic tight R-bound for aggregate queries. We plan to further extend the language to be even more expressive. We're also interested in using PC as an AQP technique. We're happy to discuss if you are interested or have any questions. Thank you for watching.